Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll discuss one remaining aspect of integration which we haven't before, and it's called definite integration. Now, everything we've studied in integration up till now falls under the category of indefinite integration, and one of the ways we can tell that it falls under the category of indefinite integration is because you always have a constant of integration at the end. For example, integral of x squared dx would be x cubed by 3 plus c, right? And c could be 0, 1, 2, pi, or any real number. So x cubed by 3 plus 1 and x cubed by 3 plus 15, both of them are different functions, yet they have the same derivative, which would be x squared. So in this case, the integral of x squared dx, or this thing which is on the LHS, is not completely definitely defined. Right, there is an arbitrary constant of integration, and that's why it's called indefinite integration. As opposed to that, when you talk about definite integration, you do know the answer once and for all. You do not have any constant of integration left. So that's the biggest difference between definite and indefinite integration. Another difference is the notation. Indefinite integration, let's just look at this, would look something like integral of x squared dx. But in definite integration, we add something else. We add two numbers at the top and bottom of the integral. Let's say it could be 2 and 5, and these are called the limits of the integration. This would be the lower limit, and this would be the upper limit. So whenever you see an integral and there are two, this could be numbers or even variables, that let's say the lower limit would be a variable y and the upper limit would be a variable z, even that's possible. So whenever you see an integral in which there are two numbers at the top and bottom of the integral, that's a definite integration, and you will not have a constant of integration in that. Now, how do we define definite integration? Well, we know for indefinite integration this formula, integral of x squared dx is equal to x cubed by 3 plus c, right? So basically, plus c is the arbitrary constant of integration, or rather c is the arbitrary constant of integration, but the integral of x square is x cubed by 3. So the value of this definite integral will be the function x cubed by 3, but it will be the difference of the value of this function at 2 points, at the lower limit and the upper limit, and we denote it by writing the limits here, which are outside a square bracket, 2 and 5. So if the integral of x square, indefinite integral of x square, is x cubed by 3 plus c, then the definite integral of x squared would be simply x cubed by 3, and you would have to take it at two limits, the lower limit and the upper limit, and this value is defined as the difference between the two limits. So this would be 5 cubed by 3, that would be 125 by 3, minus 2 cubed by 3, which would be 8 by 3, or that would be 117 by 3. And you can see here you actually had an indefinite answer. Not only was there a function, but there was an arbitrary constant of integration. Here you actually have a definite answer, and that's why it's called definite integration. So if we look at it a little bit abstractly, let's say we have a relationship between two functions, capital F of x and small f of x. And the relationship is small f of x is the derivative of capital F of x, right? From this we know integration is the opposite of differentiation, so we can write integral of f of x dx is equal to capital F of x plus c. This would be indefinite integration. This is something we've seen already. Another way we could write this in terms of definite integral would be integral of f of x dx. And now let's say we have two limits a and b, two numbers. We'll go into the application later to see why you would have two numbers here, but if we have the integral between two numbers a and b, then the value is defined as f of b minus f of a. So you simply do your indefinite integration, and by the way, here we can see why there's no constant of integration involved, right? Because it will cancel out. So let's say instead of x cubed by 3, we take x cubed by 3 plus 10, where 10 would be the constant of integration. Then here you would have 125 by 3 plus 10, and here you would have 8 by 3 plus 10. and those 10s would cancel. Or here you could say the value of this integral at b would be f of b plus c, right? F of b plus c, and then at a would be f of a plus c. And when you subtract the second from the first, c will cancel and you will get f of b minus f of a. So this is another way you can see why we don't have a constant of integration in definite integral, because it cancels out. So to repeat, the only difference between definite and indefinite integration is for definite integration, you have an additional two numbers or two variables or two values called the lower and the upper limit, and the integral is defined as the difference between the value of the integrated function at these two. So the integral of x squared might be x cubed by 3 plus c. That means the integral between 2 and 5, that's the language we use. The integral between 2 and 5 would be the value of x cubed by 3 plus c at 5 minus the value of x cubed by 3 plus c at 2. And c will cancel. This is how we write it, x cubed by 3 from 2 to 5, which gives us this value. And this is how you look at it from a generic point of view. If the derivative of capital Fx is small fx, then the integral of small fx from a to b is the value of capital Fx at b minus the value of capital Fx at a. Let's look at one or two examples of this. Let's say we were to calculate the integral of 3x squared plus 2x plus 5 dx. Right. So first let's calculate the indefinite integral. We know what that would be, x cubed plus x squared plus 5x plus c. I hope you are quite familiar and at least fast with this now, because you can do this directly, right? 3x squared will have an integral of x cubed and so on. Now what if we had this integral between two limits, and instead of taking numbers, let's just take variables or constants represented by letters. Let's just take two values a and b. We could have a is equal to 2 and b is equal to 5, or a is equal to 0, b is equal to 100, or any two numbers, right? So this was the indefinite. Now we'll move on to the definite. So if you have this, the only change is now you take the value of this function at b and the value of this function at a and you subtract them. So now the answer would be b cubed plus b squared plus 5b plus c, whatever c is, minus a cubed plus a squared plus 5a plus c, and we know c and c will cancel, so it will give me b cubed plus b squared plus 5b minus a cubed plus a squared plus 5a. And now you see, if we have two values of a and b, let's say a is 1 and b is 20, then you can have the actual value of this definite integral, which would be a number, whereas the indefinite integral would have no number because there would be an arbitrary constant of integration. Right. Now let's say we were given the question that there is a function y of x which we need to find out, such that dy by dx is equal to say 4x cubed plus 9x squared plus e to the power x. Right. And we were given, say, y of 0 is equal to 5, and we need to find y of x. So now I'm going to show you, I'll rub the upper part and I'll show you how you can solve a question like this using both the concepts of definite integration and indefinite integration. Right, you already know how to solve this using indefinite integration. You integrate it and you'll get an arbitrary constant of integration, and using what is called the initial condition, you determine the value of that constant. So using indefinite integration, what we'll get is integral of y will be integral of this into dx, 4x cubed plus 9x squared plus e to the power x times dx. And 4x cubed will give me the integral x to the power 4 plus 9x squared will give me 3x cubed plus e to the power x has the integral e to the power x plus c. So this is what we get, and now we use this initial condition. This is called the initial condition. It doesn't necessarily have to be at 0, but still it's always called the initial condition. And you need an initial condition to determine y of x uniquely. We've seen that in the previous videos on indefinite integration. So now you use this value y of 0. will give me the value when you put x is equal to 0. So this is 0 plus e to the power 0 would be 1 plus c. And we are given this is 5, which gives me c is equal to 4. Right. So which gives me uniquely y of x is equal to x to the power 4 plus 3x cubed plus e to the power x plus 4. Now we'll see how we can solve the same question and get the same solution using definite integration. So we start from this point, dy by dx is equal to 4x cubed plus 9x squared plus e to the power x, and what we'll do is take dx to the right side. So what we get is dy is equal to 4x cubed plus 9x squared plus e to the power x times dx, and now we integrate both sides. And normally what we would have done, this is the integral of 1 into dy, which would give me y. So we'll get y is equal to the other things. But because we are doing definite integration, we'll do definite integration on both sides. Which means on both sides we'll put the limit. What will be the limit? Y of 0 is equal to 5. That means when x is equal to 0, the initial condition, the value of y was 5. So the lower limit will be the same. The upper limit can be whatever we wanted, x and y. Now here I am doing a little bit of a notational error which we are not generally supposed to do, but we'll ignore it for the sake of this course. What I am doing wrong is this and this variable have to be different generally. So if you have x here, this can be some other thing z. So generally what we'll do is we'll call this variable x dash or something like that within the integral, because they can't be the same. But for now we'll ignore that. Right, that's just a notational thing. So once you have this, this gives you the integral of dy. This is 1 into dy. The integral of 1 is y. But we have two limits, y and 5. Right? So the value at y would be obviously y, and at this point the value would be 5. So the LHS would be the difference of two values, y minus 5. And again we see now we don't need any constant of integration. And the RHS would be this value at 0 and x. So this would be x to the power 4 plus 3x cubed plus e to the power x, and the limits of these between 0 and x. Actually, you know what, I'll just write this in the same way for notational consistency in this step. So this would be y between the limits 5 and y. Right? So the integral of 1 dy would be y, the integral of 4x cubed plus 9x squared plus e to the power x dx would be this term, and you take the limits on both sides from 5 to y and from 0 to x. This gives me y minus 5, and this gives me x to the power 4 plus 3x cubed plus e to the power x minus the value of this function at x is equal to 0, which is 1. And from that what I get is y is equal to x to the power 4 plus 3x cubed plus e to the power x plus 4. And we see we get the same answer. So we can either get the answer in terms of an arbitrary constant and then use the initial condition, or we can put the initial condition directly in the limits of the integration, and we won't need to bother with the constant of integration. There was no arbitrary constant in this step, right? Now there is another aspect of definite integration. Just like when we studied differentiation, there was the algebraic aspect, differentiation denoting the rate of change, and there was the geometrical aspect where derivative was the slope of the tangent. Similarly, integration also has the algebraic aspect which we've seen everywhere, and the geometric aspect, which means what does the integration represent when you draw the function on a curve, and it represents the area under the curve, right? But what we'll do is we'll study that aspect, the geometrical aspect, in the next video, which is called application of integrals, because that is generally classified in terms of application of integrals. Right now what we'll do is we'll study a few more properties of definite integrals and see how we can use those to actually calculate the values. And there are some cases where calculating indefinite integrals is impossible, but you can actually calculate definite integrals using the properties. So we'll see some of the properties and how they can be used. The first property is integral of a to b f of x dx is the negative of the integral of b to a f x dx, which means the limits are interchanged. And we can prove this quite easily. For all of the following properties, I'll assume that there is a function capital F of x such that the derivative of capital F of x is small f of x. Right. So from this what we get is, we prove this first property. The LHS is basically capital F of B minus capital F of A, and the RHS is the negative of capital F of A minus capital F of B. Remember, the value of the integral at the upper limit minus the value of the integral at the lower limit, which is again the same as this, f of b minus f of a. So the first property is proved. The second property, integral of a to b f of x dx can be broken down into two integrals where we add another limit c, which generally lies between a and b. It doesn't need to, but generally it does for applications. So we can write this as integral a to c f of x dx plus integral from c to b f of x dx. So instead of going directly from a to b, we went from a to c and from c to b. And we can prove this easily also. What is the RHS? That will be capital F of c minus capital F of a plus capital F of b minus capital F of c. And this cancels capital F of b minus capital F of a. Right? So we can see that we can break down an integral from a to b into two integrals by adding a third limit c. Another important property, the integral from a to b of f of x dx is also equal to the integral from a to b f of a plus b minus x dx. Right? So we basically change the function and replace x by a plus b minus x, where a and b are the lower and the upper limits. Now we can prove this easily. Let's take t is equal to a plus b minus x. We get dt is equal to minus dx. And the RHS can be written as the integral. Now here is something you have to remember. When you make a substitution, we've made substitutions before. Here what you would get would be f of t, and dx would be minus dt. So minus, let's say minus f of t dt. But another thing you have to change is these limits. Earlier the limits were from a to b. That means the value of x goes from a to b. So now we have to put the limits for t. So if x goes from a to b, what does t go from? It goes from a lower limit to a higher limit. And we have to put these values here. So when x is a, what is the value of t? When x is equal to a, t is equal to b. And when x is equal to b, t is equal to a. So remember this also, whenever you make a substitution and there is a definite integral involved and you change the variable, the limits have to be changed accordingly as well. Just as a simple example, if you take, let's say, sine of 2x dx and it goes, x goes from 5, let's take realistic values, x goes from pi to 2 pi, let's say. Now if you put 2x is equal to t, then the limits will become 2 pi to 4 pi, because if x goes from pi to 2 pi, t, which is twice of x, will go from 2 pi to 4 pi. So this will be sine t, dx will have to change accordingly, but these limits will also change. So remember that. So now we get minus integral a to b f of t dt, which can be written as, sorry, minus integral b to a, which can be written as integral of a to b f of t dt. And this is the same as a to b f of x dx, right? The dummy variable here doesn't really matter, whether you talk about integral a to b sine x dx, or you talk about integral a to b sine t dt. The answer in both cases will be cos a minus cos b, right? This is generally referred to as the dummy variable. Right? Just like when you use summation, sometimes you have a dummy index, here you have a dummy variable. Right? So this is a very important property which can often be used to simplify integrals. And let's look at one final property. Integral from minus a to a. Often we'll have integrals of this form from, let's say, minus 10 to 10 or minus pi to pi. F of x dx is equal to, now there are two cases here, twice the integral from 0 to a f of x dx if f of minus x is equal to f of x. This is also written by saying f of x is even. An even function is a function which follows this property: f of minus x is equal to f of x. So for example, cos x would be an even function because cos of minus x is equal to cos x. X square would be an even function because if you take minus x, the square of that is the same as the square of x. It is also equal to 0 if f of minus x is equal to the negative of f of x, and we write that by saying, you guessed it, f of x is odd. So examples of this would be cos x, x square. Examples of this would be sin x and x cube. If you take minus x, the cube of that is the negative of the cube of x. Similarly, sin of minus x is the negative of sin of x. And so if fx is an odd function, then integral from any negative value to its positive value, right? So from minus 5 to 5, or from minus 10 to 10, or from any other value will be 0. And if it's even, it will be twice the integral from 0 to a, right? And the proof is quite simple enough. We can use a previous property here and write this as integral of minus a to 0 f of x dx plus the integral from 0 to a f of x dx. And here we'll put x is equal to minus t, and we get dx is equal to minus dt. So what we get is, now x is minus t, so here we'll get a to 0 f of minus t negative of this dt plus integral of 0 to a f of x dx. We'll just write this as f of t dt too. Here we've substituted x is equal to t just for consistency. Now if f of minus t is equal to f of t, right, then we have this minus sign, integral ft dt, and the limits are from a to 0. We can put a minus sign and get it from 0 to a, so the minus sign will cancel and we get 2 integral from 0 to a. On the other hand, if f of minus t is a negative of ft, then this becomes positive integral from ft dt, and a to 0 will be the negative of 0 to a, so these two will cancel and give me the answer 0. And these properties can often be quite useful in determining answers. For example, let's say you have the integral from minus pi to pi of sine to the power 5x cos to the power 4x dx. Now if there were no limits, we still know how to do this. We take one sin x out, then we'll be left with sine to the power 4x cos to the power 4x. We can write sine to the power 4x in terms of cos square x, and then we substitute cos x is equal to t. The sin x will go into the derivative, and then we get an easy integral. So we know how to solve this before. I'm not going to do it again, but right now we can see that if you substitute in this function x by minus x, cos to the power 4x or cos to the power 4 minus x will be the same as cos to the power 4x. But sine to the power 5 of minus x will be the negative of sine to the power 4x, which means this function in the bracket is an odd function, which means the value of this integral can be directly taken to be 0. So often in entrance exams like IIT-JEE, you'll have questions like this where students will waste a lot of time actually getting the answer, but because of these limits you can actually get 0. Now if this was, let's say, minus pi to 2 pi, then you can't say directly whether it's 0 and you'll have to go through the whole process of solving it. But if it was minus 2 pi to 2 pi, we could directly write it to be 0, right? Because the thing inside the bracket is an odd function. So in the next video, we'll actually move on to the geometric application of integrals, which is the area under the curve, and we'll see some applications of calculating the areas as well. Thank you.